Hey you guys, so this is problem number 51 from chapter 4 from the section on mesh currents. And let's describe a circuit. We have a 200 volt independent voltage source and some resistors, 10, 25, 50, and 100. And here we have a current control dependent current source. So it gets its value from the current that goes through the 25 ohm resistor. So we're going to use the mesh method because this section is on the mesh. In order to solve this problem, you have to understand some key concepts. Concept number one is that the mesh method uses KVL, which is Kirchhoff's voltage law. It says that the sum of all the voltage drops around a closed mesh must equal 0. An essential closed mesh must equal 0. The second thing you need to understand is what a mesh is. A mesh is a connection of circuit elements where the beginning of the first is the same as the ending point of the last. So it makes a closed loop. For example, this is a mesh. Start here, one circuit element, 2, 3, 4. It's more importantly an essential mesh, which means there are no circuit elements contained in that mesh. This is also a mesh, but it's not a, so this is also a mesh. 1, 2, 3, 4, 5, 6, 7. It's not an essential mesh because it contains a 25 ohm resistor inside it, and therefore KVL will not hold and the mesh method will not work if you choose that as your mesh. So only essential meshes, and there's one exception. The only time that the KVL or the node voltage method will work with a circuit element is if you have a current source that borders the two meshes. For example, this is a mesh, 1, 2, 3, 4, 5. That's a mesh. This is also a mesh, 1, 2, 3, 4, 5, 6. These are two essential meshes because they don't contain a circuit element inside them. Here's also a mesh, 1, 2, 3, 4, 5, 6, 7, 8. So this is also a mesh. KVL will work here because the border of these two meshes is a current source. When the border is a current source, we call that a super mesh. And what happens is that we can ignore that and just take our mesh on the outer circuit elements because the border, the current source will have a voltage drop associated that cancels out on both sides. So that's why when you have a current source that is a border of two essential meshes, you can treat it like one mesh and just ignore that. But when we're deriving our equations, we're going to take that into account and prove that you can do that. Okay, so let's go ahead and name our mesh currents. So this mesh, I don't need to name it because the diagram has already told me this is IA. Oh, I need to tell you. We're looking for IA, IB, IC, and ID, and IE. So we're looking for those branch currents in part A. And in part B, we're going to prove that our answer is correct by showing that power dissipated equals powers developed. So our schematic has told us that this current is IA, and this current is IB, and this current is IC. That's given to us. Now we're going to write our mesh equations. So mesh at IA. The first voltage drop, remember the mesh current method uses KVL, so we're looking for voltage drops. So the first voltage drop is going to be across the 10 ohm resistor. V is equal to IR, so the R is 10, the I is IA. The next voltage drop is here, is across the current controlled dependent current source. Now again, that's a super mesh, but we're going to pretend that we don't recognize that as a super mesh and prove that it works. It has some Vx voltage drop associated with it. So we're going to say the current enters the positive terminal of the current source. So we're going to say that's going to be plus some Vx. We don't know what that Vx is. And then the last voltage drop is going to be across the 25 ohm resistor, and the net current across that is IA minus IB. All that has to equal 0. So let's simplify. 10IA plus Vx plus 25IA minus 25IB is equal to 0. 0. So then my mesh equation becomes 10 plus 25 is 35IA plus VX minus 25IB is equal to 0. So that's my first mesh equation. Now, my second mesh equation I'm going to do is going to be mesh at IC. So I'm going to start at the current controlled dependent current source. The positive current enters the negative terminal, so we've got minus Vx. So the next one, voltage drop is across the 100 ohm resistor, so that's going to be 100 times IC. And then the last voltage drop is 50 times a net current of IC minus IB is equal to 0. So let's simplify this. 100 IC plus 50 IC minus 50 ID is equal to 0. So my new equation is minus Vx plus 150 IC plus 150 IC plus minus 50 ID is equal to 0. Now, the reason why the super mesh works is, notice that in algebra we can add things together, whatever we want, right? So we can add two equations together. So what ends up happening is you got a plus Vx here and a minus Vx here, so they cancel each other out. That's why when you have a current source that borders two essential meshes, you can basically ignore that voltage drop. In this case, I don't want to ignore it because we're going to look for power, and to look for power, to find power, we have to find Vx anyways because P is equal to Vi. So I actually want to use the regular method because we're going to end up needing to find Vx. So but that is why the super mesh works, because the voltage drops will always cancel each other out. So now our third equation is going to be mesh at IB. That positive current is entering the negative terminal, so my first term is 200 volts. And then plus the next voltage drop is plus a 25 ohm resistor, so 25 is our R. Our I is a net current of IB minus IA. And our last voltage drop is across the 50 ohm resistor, and that has net current of IB minus IC. That's equal to 0. So simplifying this, we're going to put the 200 on this side, so it's going to be 2 plus 200. So we got 25 IB minus 25 IA plus 50 IB minus 50 IC. So let's start combining terms. So the IB gives me 75 IB minus 25 IA minus 50 IC. That's equal to 200. So that's our third equation. So we got three equations, but we don't have enough unknowns. We have 6 unknowns in this problem. So we need to come up with 3 more equations. So they're going to come from the constraint equation. They're going to come from ID, IE, and 4.3 ID. So the ID is a net current of ID is a net current of IB minus IA. Now we're going to rewrite that with everything on one side. So that's going to be ID minus IB plus IA is equal to 0. That's how we're going to rewrite that. That's going to be ID minus IB plus IA is equal to 0. Now, our next constraint equation is going to be IE. So we got IE is equal to the net current of IB minus IC. So rewriting that, we're going to go IE minus IB plus IC has to equal 0. And our final constraint equation is going to come from the current controlled dependent current source. Its net current, so we got 4.3 ID is equal to IC minus IA. So rewriting that, we got 4.3 ID minus IC plus IA is equal to 0. So now we got 6 equations and 6 unknowns, and we can go ahead and solve this matrix or this problem. So we got IA, IB, IC, ID, IE, and VX. And that's going to equal some constant. Okay. Our first equation, we got 35 IA, 1 VX, and negative 25 IB. All that is equal to 0. And then 0 is everywhere else. Take a second to double check. 1 VX, okay. So that's this one. Our second equation, we got negative 1 for VX, 150 for IC, and then we got negative 50 for ID, and zeros everywhere else. Okay. Negative, so 0, 0. 150 IC. So at 0. Negative 50 for minus VX. I have a mistake in this equation. So let's go back to that one. So that was my mesh at IA. So I got negative VX plus O. So I'm going to redo this one. Negative VX plus 100 IC plus 50 times IC minus IB is equal to 0. So I have 150. Oh, I have a typo here. This should be 150 IC. This should be distributed. This should be IB. That's the problem. I have a typo. Okay. Alright, so then this is really a 0. So 0 for ID and negative 50 for IB. And now I double check that. Negative 50, 150, 0, 0, negative 1, and 0. So that checks out in my worked out problem. So the next one we have is we got 75 for IB, and then negative 25 for IA, and negative 50 for IC, and then zeros everywhere else, and 200 for constants. Okay, negative 25. Okay, so apparently I have a typo here somewhere too, because I didn't come up. So let's just rework. So this one was mesh at 75 IB. So this must have been mesh at is equal to 2. So this must have been mesh at IB. So I have some kind of mistake on my mesh at IB equation. So let's just rewrite it. Minus 200 plus 25 times IB minus IA. Plus 50 times IB minus IC. Oh, I forgot the little resistor at the bottom. Plus 10 IB is equal to 0. That's what happened. I forgot the little resistor at the bottom. I forgot this one. Everything else is correct, but I forgot that one. So that would make this 85 IB. So let's just account for that. I've got 25 IB here, 50 IB here. So that's 75, and then I forgot about the little one guy at the bottom, so that makes this 85 IB. So then this should be 85, 85, and I've got negative 25, 85, negative 50, 0, 0, 0, and 200. Okay, so now that checks out with my pre-worked out problem. So then the next one is we got 1 for ID, negative 1 for IB, 1 for IA, and zeros everywhere else. So 1, negative 1, 0, 1, 0, 0, 0. Let me erase that. And then our fifth equation is 1 for IE, negative 1 for IB, and 1 for IC. Zeros everywhere else. So 0, 0, negative 1. So I got negative 1. Okay, so that should work. And then the last one is I got 1 for ID, 1 for negative 1 for IC, and 1 for IA. Oops, 4.3 for ID, excuse me, 4.3. That should be 4.3. So negative 1, positive 1, and negative 0.3. Okay, so now we're going to put this matrix into our equations, our simultaneous equation solver. So this is a 6 by 6 matrix. We got 35, negative 25, 0, 0, 0, 1, 0. 0, negative 50, 150, 0, 0, negative 1, and 0. Negative 25, 85, negative 50, 0, 0, 0, 200. 1, negative 1, 0, 1, 0, 0, 0. 0, negative 1, 1, 0, 1, 0, 0, and 1, 0, negative 1, 4.3, 0, 0, 0, solve. Okay, so let's see if I got the same answer as I did before. Okay, I1, 2, 5. 4.6, 0.97, negative 1.1, 3.63, and negative 84.5. Okay, so got the same answer as before. So our solution is, and the answer to part A is IA is equal to 5.7 amps, IB is equal to 4.6 amps, IC is equal to 0.97 amps, and ID is equal to negative 1.1 amps, IE is equal to 3.63 amps, and VX is equal to negative 84.5 volts. So that is the answer for part A. Now, in part B, we need to prove that our answer is correct. And we're going to do that by showing power dissipated is equal to power developed. So we have to find the power of every circuit element, which is why I didn't want to use a super mesh, because I knew that we would need the voltage drop ultimately. So we have 7 circuit elements. Let's start one by one. Power of the 200 volt independent voltage source, that's just V times I. The V, the current is entering the negative terminal, so that tells me the V is negative 200 volts, and the I is going to be IA. So, and IA is 5.7 amps. Wait a second. IB, pardon me, that's IB. So IB is 4.6 amps. So that's going to give me power of negative 920 watts. So that's negative power means that the circuit element is generating power, developing power. So the next one is going to be the 25 ohms. So P is equal to I squared R. The R is 25. The I is a net current of IA minus IB. So actually it's ID, right? Because we found that. So ID is negative 1.1 amps squared. When you do that math, you should come up with 30.25 watts. So P of 10 is I squared R. The R is 10. The I is IA. So that's going to be times 5.7 squared. And that gives me 324.9 watts. The next one is P, the power dissipated by the 4.3 ID current controlled dependent current source. That's going to be the Vx. The net current enters the negative terminal, so negative times a negative Vx. So since Vx is negative 84.5, that's going to be positive. So a negative times a negative is a positive, so that's 84.5 volts. The current value, it's a current controlled dependent current source, is going to be 4.3 ID. So that's going to be 4.3 times ID, which is negative 1.1 amps. So that should give you negative 399.685 watts. So that's circuit element generates power. So the next circuit element is the 50 ohm resistor. So that's going to be I squared R. The R is 50. The I is going to be IE. So that's going to be 3.63 squared. So that gives me 658.845. I have two more circuit elements. So the next one is the power across the 10 ohm resistor. So P of 10, that's going to be, so that 10 ohm resistor is going to be I squared R. So the R is 10, the I is IB, and IB we said was, IB we said was 4.6. So that's going to be times 4.6 squared. And that should give you 211.6. And the final circuit element is the 100 ohm resistor, so that's I squared R. The R is 100, the I is IC, which is 0.97 amps. So that should give you 94.09 watts. Okay, so now we're going to make a table. Negative power is power dissipated or developed by a circuit element. Positive power is power dissipated by a circuit element. So let's do some accounting. The first circuit element has negative 920, so we're going to put 920 here. 30.25, 324.9, and then 399.685. And 658.845 to 11.6, 94.09. And when you do the math, 30.25, 324.9, 658.845 to 11.6, 94.09, 920, 399, you should come up with 19.685. And 19.685, and that proves that power dissipated equals powers developed, and that proves our answer was correct. All right, make sure to share the video on Facebook, like the Facebook link to the page, and above all, help other people.